Łukasz, możesz coś powiedzieć jeszcze na chwilę testowo?
Raz, dwa, trzy, mówię. Raz, dwa, trzy.
Słuchać?
Ważne, żeby Dawida było słychać.
Słychać mnie?
Dawida, słuchasz lepiej, tak.
Okej. Prezentację widać?
Tak, widać, widać.
Można zaczynać.
Welcome to today's seminar. Our guest is Dawid Mozdzierski, who is an assistant professor at University of Wrocław. He will tell us about variable stars in open clusters. Dawid, the floor is yours.
Thank you. Thank you very much. Good afternoon. So my name is Dawid Mozdzierski, and I'm glad that I can introduce you to my research on this seminar. And thank you very much, Łukasz, for the invitation. So I would like to introduce you to the topic of variable stars in open clusters and convince you that they are very useful tools for understanding the structure and evolution of stars. So I'll start with open clusters. As we all know, open clusters are groups of stars of irregular shape, usually a few hundred to several thousand members. These are young objects, usually much younger than 1 billion years. And what we like in open clusters, what people who study stars like in open clusters are three very useful assumptions for cluster members. So we can assume that for the cluster members that they are on the same distance to the observer, because the distance between cluster members are much smaller than to observer. They share the same chemical composition and the same age, as they all form in one big molecular cloud. We can, with open clusters, we have a possibility to study stars in the wide range of masses. So on the left side, we can see the quite famous plot of main sequence of different open clusters. And as we can see, they are sometimes open clusters contain very massive stars like H and He Persei, like NGC 4755. And we can observe also open clusters, very pretty old open clusters like M67, where we can study much older and much less massive stars on late stages of evolution. M67 is similar, in fact, similar like a globular cluster, for example. Of course, we can study these stars with models, usually with isochrons. On the right side, we can see some plots for NGC 457 open cluster when we fitted the isochrons for different chemical metallicities, and we obtained different ages for these different fits and different distances. So these are such examples. We are focusing on open clusters containing massive stars. So we are looking for young open clusters, usually younger than 20 million of years, and clusters which possibly contain many massive pulsating stars. So clusters when we can see many bright members. But why massive stars? So there are many good reasons for studying of massive stars. They have significant impact on the chemical evolution of the universe. with their stellar winds, and of course with products of supernova explosions, because they are finishing their life as supernovas. And because of extremely high temperatures and pressures in massive stars' interiors, we have a possibility of testing the physical and chemical properties of matter in conditions unreachable in Earth laboratories. But at the same time, the evolution of such massive stars is relatively fast in the scale of the universe and on the scale of life of other stars. And the more massive is a star, the faster its evolution is. So it makes the most massive of these stars very elusive objects. They are not common, in fact. And unfortunately, there is too many open questions about massive stars. So we have problems with rotation. We don't really know what is the exact mechanism of angular momentum transport from the core to the envelope, which we we suspect that there should be efficient angular momentum transport, but we don't know what is this exactly. We suspect that also we have pretty big mixing of chemical elements because of rotation, and this has big influence on evolution rate of these stars. And evolution in binary systems is also very important, because we know that massive stars are mainly binary stars. So eventual mass transfers, we want to know how efficient these mass transfers are, and we want to know how accretion disks works, and what is the efficiency of accretion of the mass. And this has impact on evolution rate. And also, it's pretty hard to recognize mergers of stars. Also very important is mass loss rate, especially for massive stars above 60 solar masses. So the stars close to the Eddington limit. Stellar winds are important during a main sequence stage of such stars, and also after main sequence. And this has also connections with evolution rate, and also with angular momentum loss. In interior of stars, we have many questions about the processes inside the stars. We don't know how really works overshooting from convective core, and this has also a big influence on evolution rate of these stars. And microphysics, as we can see, as we will see later, we have pretty big problems with opacity tables, and these problems emerged from investigations of pulsating stars. And in all of this, there is also unclear role of magnetic fields. We suspect that they are important, and they have impact on every above problems of massive stars, but we don't really know how big is this impact. Of course, one of the best, of the most promising method of investigation of interiors of stars is asteroseismology. Fortunately, many massive stars are pulsating stars, beta Cephei stars, and SPB type stars. But in fact, now we can see pulsations on many stages of evolution. Maybe in the future we will be able to observe some kind of pulsations on any stage of evolution, which is very good for research. And if we have pulsating stars in open cluster, then we have possibility of so-called ensemble asteroseismology. But the question is, which open clusters are good for such research? So we have looked for some open for variable stars in some open clusters, and we tried to span wide range of ages from the most younger to the older clusters, and what we have found. So in case of IC 1805, this is very young open cluster, and we investigated the central part of this cluster. This is central part of so-called Heart Nebula, visible on the left side. And on the right side of this slide, we can see what we have detected. So this cluster contains many massive stars, and because of very young age, it's turned out that most massive stars are variables, are irregular variables, marked here with orange circles. But we found only 2 beta Cephei stars, which are marked here with blue circles. And not even one SPB star for this cluster. What is interesting, we've detected almost 30 monoperiodic variables with periods from half to 8 days in the lower part of the color magnitude diagram. They can be seen here on the right side, and going back to the beta Cephei stars, it was hard. In fact, it was hard to detect these beta Cephei stars because their amplitudes were very small. Are very small. We found also some delta Scuti stars, but probably 2 of them are just field stars, and one of them is maybe pre-main sequence stars. And these monoperiodic variables, we suspect that they are also pre-main sequence stars with spots on their surfaces. And this is not, and this is something what we observed before for another very young open cluster, NGC 6823. Andrzej Pigulski, Zbigniew Kołaczkowski, and Grzegorz Kopacki detected some such monoperiodic stars in this cluster also, and they are located in the similar place on color magnitude diagram as for IC 1805. And later, this cluster was investigated also by Ewa Zachajkiewicz. On the left side, we can see that this cluster is inside the nebula, so very young open cluster. On the lower panel, lower picture, we can see the image and Cusin's filter, so in infrared, and this is a stack of many pictures with total exposures of many hours. So we detected there are many stars. And we were searching also for beta Cephei stars, for massive variable stars in a bit older clusters, as I said before. So the next cluster is IC4996. Its age was estimated for 9 million of years, but it should be checked because for this cluster we also found this monoperiodic stars in lower part of color magnitude diagram, or again with very similar periods as for the two mentioned before open clusters. And this time we also found 2 beta Cephei stars, and we detected 6 SPB stars. So it looks like this cluster is really a bit older than IC 1805, but maybe not the best one for the existence of beta Cephei stars there. There is much more delta Scuti star detected. So here, this is an example of open cluster with pretty high number of pulsating stars. And what we suspected that with these monoperiodic variables, we can in future investigate the evolution of pre-main sequence stars, and this is work for the future for us. So its variability is good. It should be good tool for investigation of pre-main sequence stars. We also made a variability survey in NGC 457 cluster, which is a bit older cluster than all of clusters before. This cluster is pretty good known for amateur astronomers as ET cluster because of its shape, or as the old cluster and 2 mice, as can be seen here. This cluster has, in contrast to the clusters which I showed before, a very small different reddening in the field of observations, and this can be recognized by the observed main sequence of these clusters. It's very tiny. It's very tight main sequence, not smeared like for IC 1805 and IC 4996. And we conclude that such cluster is a bit too old for beta Cephei stars. We've found there 1 beta Cephei, but only 1. But interestingly, we found there also 21 SPB pulsating stars. And what was surprising, they show frequencies higher than 3 cycles per day, even to 7 cycles per day, which is pretty uncommon for SPB stars. But we are sure that they should be SPB stars, as they are late B-type stars. Their spectral type is not suited for the beta Cephei stars. On the left side on the slide, we can see schematic frequency spectra for these SPB stars with the 1 beta Cephei stars on the top, and they are arranged from the most luminous to the faintest of stars, so from the higher mass to the lower lower mass of this sequence. And we can see that some of these frequency spectra, especially the star 88, 3 and 117.26, has frequencies as high as almost 7 cycles per day. So we suspect that these SPB stars are just very high, has very high rotational velocities. This is why we observed such high frequencies, but we can see that it's not straightforward to recognize a beta Cephei star just from the frequency spectra. Okay. And finally, there is we investigated NGC 6910. It turns out that this cluster is just the right one for the existence of beta Cephei stars. This cluster is in Cygnus constellation on a distance of about 1.5 kiloparsec with a pretty big differential reddening because of nebula. And Zbigniew Kołaczkowski in 2004 found there 4 beta Cephei stars. So we have a great chance for ensemble asteroseismology of massive stars here. Later was conducted a pretty big observational campaign, and Sesson et al. In 2010 published paper when they informed that they detected 9 beta Cephei stars. So we continue this observation campaign. We got new photometric observations and spectroscopic observations, mostly from Poland in Białków, from Xinglong in China, and from La Palma from telescopes Mercator and NOT, from APO in New Mexico, and from France. In the result, we found 73 variable stars in the field of observations of this open cluster. And on the right side, we can see its color magnitude diagram. It's pretty hard to recognize here the main sequence of NGC 6910. It is because of this high differential reddening, and top part of color magnitude diagram looks a bit like a fork, and the left side of this color magnitude, on the left side we have field stars, and on the right side here we have a main sequence of the NGC 6910 cluster. The variability picture here is pretty rich. It's like the hybrid of young and a bit older cluster, because we have here very massive young stars with irregular variability. We have 8 beta Cephei stars, also SPB stars, these green circles, and some and maybe one delta Scuti star is a member of this cluster. But we have also in the very low part of color magnitude diagram these monoperiodic variables, and it's pretty big population, 34 monoperiodic variables, again with well-known periods from the other clusters, from half day to 10 days. So it was even better for ensemble asteroseismology after this research. In the result, we detected 40 frequencies for all 9 B-type pulsating stars, for which we made also spectroscopic observations. 37 intrinsic, 2 harmonics, and 1 combination frequency. And on the right side, we have a panel again with schematic frequency spectra from arranged from the most luminous to the faintest star. And what was mentioned in work of Sesson et al. In 2010, they are we can see the progress of modes from the most massive to the less massive stars. And this is what we expect for P-modes pulsations for such stars. We also detected some changes in amplitudes of these modes, because observations span range from 2005 to 2013 year. So we have possibility to investigate this amplitude changes. These are visible on in the center plot. One of mode changed really significantly, about 3 times. It was for star number 27 here. And we can see that, for example, star number 18 has modes which are pretty stable for all of these observations. And this is the star with the most, with the richest frequency spectrum in all of these stars, from all of these stars. What is the problem? The main problem in asteroseismology is a correct identification of modes. We want to know what we see on the surfaces on the stars, what kind of pulsations. We coded it with LMN numbers, and we want to know the values of these numbers. And it's hard to find what we see exactly, because we are not able to see surfaces of the stars, and we have to use some clever methods to identify these modes with photometric and spectroscopic observations. Ensemble asteroseismology. So asteroseismology in open cluster of many pulsating stars can make this easier, because we can omit sometimes the complications connected with identification of modes. How we define the ensemble asteroseismology? It's simultaneous seismic modeling of more than one star, which uses constraints on parameters resulting from the membership of these stars to a distinct stellar system. And there is no one way of ensemble asteroseismology. There were some approaches before for massive stars like beta Cephei stars, for delta Scuti stars, and for red giants, which show solar type pulsations. In our approach, we are constraining a cluster age and mode identification of pulsating stars. So we are constraining these two things at the same time iteratively. And the constraining of identification of pulsating stars modes we called ensemble identification. This is the mentioned before guessing of identification of modes, and how it really works. So we started from so-called error boxes. So the parameters of our B-type stars from photometry and from spectroscopy. But and then we can see here these error boxes on this plot. Then we search for seismic models, which were seismic models which can describe the observed variability of pulsating stars. And the best candidate to start this process was star number 18, because we detected there we identified for this star radial modes, and seismic models of these radial modes are visible here. And we constrain the amount of these modes of these models for this mode with temperature, with error box, with temperature of star number 18. But we didn't rely on log G, because we didn't really trust for the values of log G, which we got from the photometry and spectroscopy. But it turns out that temperature is enough to constrain, significantly constrain seismic models. With these models, we got first approximation constraints on age for these stars, so automatically for all of stars in this cluster. Then we were able to use this constraint of age for the seismic models of other stars. And for 16 and 14 star, we got these models constrained with age of models of star number 18. And in case when we can get a much better constraint of age from the seismic models of other stars, we can come back to the stars modeled before, like the star 18, and constrain again its models. So this is the iterative process, and during this process, we can got for every star constraints of seismic models. So for the most massive stars, constraints were pretty wide, unfortunately, but for less massive stars, the constraints on seismic models were much better, like for 41 star and 34 star. These are really small ranges of parameters in this plane, log temperature and log G. And also we got constraints for the 38 and 36 star. The details of this modeling were described in our work in 2019, published in 2019. On the right side, we can see color-coded eta parameter, which is the excitation parameter of excitation of modes, and the modes are excited where we have eta bigger than 0. And as you can see, for stars of lower masses, like 34, 38, and 36, all modes are stable. So our models, including our opacity tables, are not good for these stars. And this is known problem from other researchers, asteroseismic researchers of other stars. So there is need for opacity tables revision because of this stable modes. And after 2 iterations for NGC 6910, we got the age for this cluster for about 10.6 millions of years with a pretty small error. For example, if we compare it with conventional isochron fitting, we can see that difference is really big, because usually we can estimate the age of the young open cluster with 30 to 50% errors. So these are big errors. Of course, we should treat our results with some with some attention because additional attention because these are our research is based on models in many on many stages of this process. So if we change a bit models, if we will get better models of oscillations and maybe better opacity tables and so on, then we will possibly we will get a bit a slightly different age for this for the cluster. So this method, this ensemble asteroseismology method, is something like the presentation of potential of this method. What was surprising from our research is that we found beta Cephei star with unusually a small mass, lower than 6 solar masses. And sometimes for some of stars from NGC 6910, we also been able to get some constraints on overshooting from convection core. These are not really strong constraints, but hopefully in the future we will be able to improve these parameters. At least we have some constraints on this parameter. As I said before, we found this very low mass beta Cephei star, which is marked here. So we have here the instability strips of SPB and beta Cephei stars. So state-of-the-art instability strips computed on OP-LIB opacity tables. And as you can see, our beta Cephei is out of the beta Cephei instability strip. So with this research, we can make the revision of instability strips. It's a problem for theories for astronomers which are calculating instability strips. The work is ongoing. Now we are investigating NGC 637 cluster, which is known as one of the richest in beta Cephei star on northern hemisphere, because in 2011 Hunter and Mengest detected there 4 beta Cephei stars and 1 suspected beta Cephei. So we made more observations in Białków Observatory with our telescope, favorite telescope in Białków, 0.6 meter. And also we got some observations from USA, from Kitt Peak, 1.3 meter telescope, and from Xinjiang Astronomical Observatory in China, where was used 1 meter telescope. And what we have now is analysis of variability, analysis of Białków data. And in this data, thanks to this data, we detected 39 variable stars in NGC 637, and not even 1 monoperiodic star in the lower part of this cluster. So a bit different situation in every open cluster before. As we can see on the left panel, again, this schematic frequency spectra observed for the cluster members, for pulsating cluster members, are not so well arranged, there is not visible this progress of modes from the most massive to the less massive stars. They are pretty in the same place in case of frequencies. But if we can, if we see the color magnitude at the location of beta Cephei stars which are observed there, then we can see that these are pretty similar stars of pretty similar mass and brightness. Thanks to the more observations than published by Handler and Maingast, we were able to detect more frequencies for these stars. And what is especially interesting is that some of the stars has really big amplitudes, like NGC 6374 has amplitude as high as 66 millimagnitudes. So it's one of the highest amplitude of beta Cephei star observed. And again, this star has interesting frequencies, because if we look closer to the frequencies, we will see that the differences between some of them are pretty the same. So we can suspect that we have here maybe a triplet of for example, rotational split triplet of modes. And this will be investigated by us with ensemble asteroseismology. We'll try to find the answer. This is on this schematic frequency spectra. These are those here frequencies, so in very close group. And we have also more targets for which we have observations, and we are still making observations. We have observations for the Southern Hemisphere open cluster, very well known for the high amount of beta Cephei stars, NGC 3293, in Carina constellation, and for famous double cluster in Perseus, NGC 884 and NGC 869, where find 11 beta Cephei stars and 9 beta Cephei stars, also with the campaign conducted for NGC 6910, so published in this paper of Season et al. In 2010, and from the research of Majewska-Świerbinowicz from 2008. We have also very interesting data for Westerlund 1 cluster, for which we will publish the results hopefully pretty soon. So in summary, we can say that open clusters are really great laboratories of stellar evolution, especially when paired with variability surveys. Thanks to geometric variability, like eclipse phenomena and stellar spots transits, we can study binary systems. We can, for example, estimate their masses and use this estimate of mass for the rest of the stars in the cluster, because connecting it with, for example, isochron, which is most common way, we can investigate the evolution of prime sequence stars and many more. In the case of detection of many pulsating stars, we are able to carry out ensemble asteroseismology and get constraints on stellar interior parameters. And even we can get some hints on the nature of the physical processes taking place deep inside stars. So we hope for some hints on internal rotation. So also for angular momentum transfer, and of course opacity tables. These are things which can be studied with methods which I described. And common characteristics of stars resulting from belonging to the same cluster make asteroseismology and other methods which we use for open cluster easier than in the case of a single star, because we have more constraints. So this is all what I wanted to show you today. Thank you very much for your attention.
Thank you, David. Questions? Do you have questions, David? Audience? Can you come closer?
So I have two questions. First, one of the color magnitude diagrams presented a star marked as SPBE. So the question is, what are these stars?
It was somewhere here.
It was the cluster with the very tight main sequence, I think.
Okay, NGC 457. Okay. Yes. Yes, we make this classification for the star, which has observed high V-sin I parameter. So it was more than 300 kilometers per second. So this is the star marked with red bars on the left panel, 5943. And we observe for this star emission in H alpha. And also in literature, we can find estimation of V-sin I parameter for this star. So we, for the needs of our work on NGC 457, we called it, we identified it as, we described it as SPBE star. So it tells that this is a star with emission and with high rotation.
Okay.
And with high frequencies.
Okay, so the second question, you said that there were two iterations for the cluster that you described
Yes.
for this ensemble sampler, ensemble asteroseismology. So what is the difference between these iterations? Do you pass information from like last of the stars models to the first one back somehow? What are these iterations?
Yes, so the second constraints came from the star number 14, and because interestingly for this star we didn't identify the modes because of possible okay, I don't remember now. Okay, it wasn't good. The identification wasn't good for this star, and here are marked with gray symbols evolution models of these stars. So we have much more models than we might get if we had the oscillation models. And despite that we have much more models, this evolution models gave us the second constraint of H. So when we got constraint of age from star number 18, we use it for evolutionary models of star number 14, and it turns out that we have evolutionary models in the smaller range of ages than for 18. So we came back to the star number 18 with this new constraints of age. And we use it also for the rest of seismic models of observed stars.
Other questions? Łukasz, I see your raised hand.
Yes, thank you very much, David, for this talk. I have kind of two questions, but they are related. So is blending an issue for you? Because these clusters, even though they're open, they're still quite crowded. And especially at the faint end, you might get some blending, which then you can run into problem. Are you actually tracing the real variability, or is it the blend or stuff like this? And the related question is, would combining data with other telescopes is possible at all? And or is it going to be more painful than, or you prefer working on the same telescope with a consistent data set? What's your say on this?
Okay, maybe from the first. Yes, there is also a risk of this that we have in fact two stars, because massive stars are frequently binary stars. So we have to. This is the caution for us, that these results might have problems with blending of stars. But okay, I think that we will, if there were really blended stars, we might find it at least in spectroscopic observations. And we, for NGC 6910, we have many spectra for some of these stars. So we were pretty safe with this. And the next question, generally, it might be a bit more painful, but there are known examples of analysis of stellar variability, pulsating stars, which showed that it's worth to analyze more data. It's sometimes. It's not always, but sometimes it can show some problems with variability, like changes of modes, which is also valuable because we don't want to investigate problematic modes, which we don't really know what is going on with them, and so yes, in the future investigations of our targets, I hope for get observations even from also from BHTOM, as we talked before. So I'm working now on the proper list of targets for this, and yes, I think it will be valuable to get more observations from more telescopes, especially for bright stars, because we don't need sometimes photometry for all of these stars, the faint stars and etc., because our beta Cepheid stars are the brightest ones usually, but not always.
Great, thanks.
Okay, I don't see any other questions on Zoom, so let's thank our speaker again.
Thank you very much.
Really?